Hey guys, welcome to 6 for Band 6, episode 2. We are looking at networks today. So what I'm going to do, once again, we're assuming that you know the basics of networks, and I'm just looking at these HSC style questions. I'm focusing today on the critical paths topic, okay, just because it's the more difficult one by far. I find this one quite challenging. So let's have a look at these HSC problems. I split critical paths up into two different parts. The first part, it talks about your immediate predecessors and backwards and forward scanning. The second part is about your flow and the cut capacity of real life applications, which is, both of them are quite difficult. So let's have a look at these questions. So the first one here is a multiple choice question. Basically, it says which one of these graphs out of these four represents the table here. The first thing I say is anything that has no immediate predecessors means that it connects to the start. And anything that are not immediate predecessors connect to the end. So what I then do is I count through and see what one of the activity letters are not in the immediate predecessors. So I got A, B, C is there, D, E, F, G, H, I. So what's missing on this side is J, which means J is the only one that connects to the finish. So the first thing I'm going to do, because I'm trying to avoid, I could sit here and draw that entire activity chart and immediate predecessor in my own network, but the thing is, I'm trying to avoid that. It's going to take longer. So let's see if I can knock any out. I need A, B, C to connect to the start, which they all do. But I need only J to connect to the end, which eliminates C straight away because it has H and J connecting to the end, which is not the case. So that's the first thing. The next thing I'm going to do is go, okay, now I need to actually look at these immediate predecessors and see where there's an error in some of them. The first thing is we could do is, let's say, looking at the three that's left, they all have I, okay? The dot right before I is going to where all I's immediate predecessors lead to. And they all look very different. So that is a good starting point, okay? Something I'm not going to do is like look at the immediate predecessors of D, say, because the immediate predecessor of D for all the leftovers are all the same. So let's look at I. Now, let's see what I is meant to have. The only immediate predecessors for I is meant to be F and G. So let's have a look at this first one here. The immediate predecessors of I, well, it is definitely F, but G is not one. It needs to be directly linked to it. So that knocks out A, okay? So now let's look at B and D. Immediate predecessors of I for B are G, E, and F. And that means that, what one was it? G, was it G? No, E, sorry. E is not an immediate predecessor to I, so that line isn't meant to be there, which eliminates B. So the answer for this one is D. So it's just about a process of elimination for that one. Okay, let's keep going. All right, identify the critical path. A critical path is a network with zero float time, so zero float time. Now, everyone does forward and backward scanning differently to some extent. You guys in my class, we looked at it with our rectangles. So we drew rectangles for however many immediate predecessors they had. So basically, if it has two arrows coming in, I need two rectangles, two arrows coming in. And the final one, I usually, you can get away with one, but I'll do two. I'll stick with what I'm saying. So two arrows coming in, two. So then I'm going to go through and go, okay, so this is the start. This is for D. This line over here is linking from E. This rectangle links to F. This one's G, so hopefully you can see what I'm doing. I got I and H there, because I is one path, H is one path, and J and K. So I've kind of just linked so I can clearly not make an error on accidentally mixing up my boxes there. So let's start with forward scanning. So we've got 0 to start with. They told us no difference. Now remember, forward scanning, we are plussing and we take the largest number each time, okay? All right, so let's have a look. 11, I'm going to add, again, assuming you know how to do this, take 11, add 16, gives me 27. Take 27 and add 8, gives me 35. Take 11 and add 10, gives me 21. Take, now at this point here, as I'm going from here up or here down, I need to take the largest number because technically this dot here connects to both of those rectangles, and this is where I take my largest number. So this next one, to go down to H, I take 27 and I add 3, it gives me 30. So when there's two options, you need to take the largest one when we are forward scanning. Okay, but it was 35 plus 1 gives me 36. Again, I've got two options now to press forward to K. I take the biggest one out of H and I, which is I's, and I plus, which gives me 45 here. 35 plus 10 also gives me 45. So now, backward scanning, I'm going to start with my end time. Now I just do the exact same thing. Going backwards, I'm subtracting and I take the smallest number this time. All right, smallest number each time. All right, let's see what we get. I'm just going to fast forward a little bit here, just so you can have a go at filling in this and make sure your numbers are the same. Okay, so if you have backward scanned, you would get these numbers. Be careful, I saw an easy error to make here. This was I, so when you had to backward scan, you had to come up from G and then subtract 1 down here to get to the I. Okay, so now they could say, what's the float time of I? And you could say, it's 2. What's the float time of H? It's 6. That's the benefit of having those many rectangles. Now, all we need to do is find the critical path. Remember, a critical path is where there is a 0 float time. So my 0 float time is looking at all of the rectangles. And now let's see what that is. So that is the path D, E, G, J, which is A. So there, oh, actually, hang on a second. We have, what's happened here? Yep, no, that's definitely correct. They actually have an answer. I took this from the Smarter Maths program, and their answer, looking at it now, was D. The only thing with D's though is if they had 36 here. Let's say they did have 36. When you're doing a critical path, you want to get through as many of the vertices as possible. So see how that would become a critical point? I would become a critical point. So you would actually go G, I, K. Okay, so that's how they get that extra one. But they haven't followed the correct path back and realized that that should actually be 34, which is a mistake I made. Okay, so the answer is A for that one, in fact, not D. Okay, let's keep going forward. All right. Now this is just an application of these. So I'm just going to go through this relatively quickly and talk about what you would do. So basically we've got this, talks about activities for a project and the times in hours. Part 1 says find the number of activities that have exactly 2 immediate predecessors. So to have 2 immediate predecessors, I just need 2 lines coming into it. All right, so let's have a look. So not this vertice, obviously not the start. So I'm just crossing off all the things. Here we've got one, it's got 2 coming into it. And we got one here, 2 coming into it. Not that one. This one's got 3, so it's not that, it's not that. So what have 2 immediate predecessors? I and J do. All right, critical path. So once again, you're going to forward scan, backward scan. If you want to, pause the video now, have a go at doing your own forward and backward scanning and see how you go with it. It does take a little bit of practice to get it right. So pause the video right here and give it a go. I will too. All right, flew through that, but we've got all our forward and backward scanning done. Some of it was a little bit tricky, so let's see now. We need to find the critical path. Critical path is going to have no float time. So what if, oops, ignore that line through there. I should have a highlighter on. 0, 0, 3, 3. So I'm just going to go through and highlight everything. There we go. That's all of them. So now my critical path is going from A, B, E, I, L. There is my critical path. Oh, sorry, not A. Not including A. A is the wrong way. So starting at B, we don't need to start at A. I was thinking the start was A, but nope. B up to E, I, L. That is the critical path. All right. The last one is just something that complicates things a little bit. I'll quickly have a look at it with you before we go to the other parts. It says E is reduced by an hour. So now we have, instead of 5, we have 4. Okay. Then it says identify the 2 new critical paths. So this changes things. Okay. So let's think about what it's changing. 3 plus 4 now instead of plus 5. So that makes a 7 here. Then plus 4 gives me 11, which makes 19. So now what happens, nothing else changes, but now I have 19. I could write this around it. 19 minus 8 gives me 11, 11, 11. Notice now we have a new critical point here. 11 minus 3 gives me 8, a new critical point here. So what you're going to find is as you keep going through, you've got these new critical points. You'll find here this is also one. So what you will find is there are now 2 other critical paths based on those new critical points, which are these. Okay, so it's only 1 mark because it's not too bad. It's just manipulating a couple of numbers. All right, the next part. This is the big stuff. Flow and cut capacity. A few definitions to start with. First thing, source is the start of the network, okay? So whatever you've got happening around your network, your source is at the start, sink is at the end, okay? Source, start, sink, end. Now, usually what they have along the edges of these networks that are more application edges, they're talking about flow. So it's, you know, how many cars can travel along this road or how much water can fit through that pipe. So they have values on them, okay? A big one is water in the pipe, okay? So what happens is if, let's say 10 litres per minute can fit through this pipe here, but 5 litres per minute can only fit through this pipe here, and then we'll go 6 litres per minute can fit through this last pipe here. What we say is, well, 5 is the most that you could fit through the entire pipe flow, okay? Because it's going to explode or bottleneck this pipe if they send through too much water. So the maximum flow capacity along this whole thing is going to be 5 because it's the smallest one. You can't fit any more than 5 in here, so you're not going to fit any more than 5 all the way through. So what that means is 5, this here is at its capacity. So it's where its maximum possible flow is flowing through it. So we call this a saturated edge, okay, which is where this definition comes from. So a saturated edge is an edge that has its peak flow. And I've said here, number is equal to greatest new number, and you'll soon see what I mean by that, but see how the number I've written here was the maximum flow of every edge, the 5. And it's the same number as what was originally there, saturated edge. But we will look more into that in a second. So maximum flow, it's the flow of the smallest pipe. So the maximum flow for that entire sequence there was 5 because it was the flow of the smallest pipe. We can do cuts. Cuts are imaginary lines that would disconnect all flow of water or cars, whatever we're talking about, from the source and the sink. So it's one cut. You want to try and cut through the least amount of pipes as possible, but still manage to get all water restricted. So a cut capacity is basically the addition of the edges that the cut passes through. Okay. Now, a minimum cut is the cut, so there are many cuts. So in this very ugly looking original network I put up here, it's cleaned up a bit, I put a cut through the first two here, but I could have also put a cut through the last two, or a cut through that middle and the last one there. So there are multiple cuts. So a cut capacity, a minimum cut is going to be which one of these cuts, when you add up all the edges it passes through, is the smallest. So that's all that means. All right, now the maximum flow of the entire network, I should say, is always the exact same answer as what your minimum cut is. So whatever the minimum cut here is, the smallest cut, it's always going to be the same. So here I had 5 was our max flow, remember? So if all the rest of this network had values, when you added it up, found your minimum cut, the answer would be 5, wherever that minimum cut is. It's just a little formula to remember. I'll come back to this little diagram here with the car, or it's meant to be a car, and show you what that means soon. Let's jump straight into some questions together though. Now don't forget, this stuff is difficult. If you find it hard to get your head around, don't stress, because so did I. Let's have a look. In this directed graph above, the weight of each edge is non-zero. Okay, thanks for letting us know that. The capacity of the cut is shown is, now, when you do a cut, the rule says from the bottom of the cut up to the top of the cut, and this is in that video that I gave you guys to watch for your Flexi Friday when you learn about this. Draw a little car. When the car travels up through the cut, the edges that you count in your cut are the edges where the edge or the arrow comes through the passenger door and out the driver's door, which is what my little diagram here meant. Okay, so I put it a tick because we count it if it passes through the passenger and out the driver. We don't count it if it goes through the driver and out the passenger. We don't count that edge. So it's just a nice little trick to remember whether you count the edge or not. So let's have a look. This here passes through passenger, out the driver. So tick, yes, we count that. So we go over here now, the car's here, passing through the passenger, out the driver. Yes, it is, because I'm looking at the way the arrows are pointing. Same here, arrows pointing, passes through, out the driver. Yep. This one here, the arrow's pointing back this way. This one would actually pass through the driver's side first, so I don't count that. And then this one here, we do count. So what does that mean? When I'm counting the edges that I'm going to cut with my line, it means that I don't need to worry about cutting the edge D, okay? It means it's not going to make any difference. And if you're a plumber and you had to restrict the water from the source to the sink, you would only need to cut the line of water through E, pipe E, C, B, and A. Cutting the pipe water through D, it's not going to do anything. There's no point in it, so don't waste your time with it. And plumbers actually use this sort of stuff when they do it. So I need, put it in order, A, B, C, E. That is the capacity of my cut. Because they want to know capacity, so with these values, you plus them all together, which gives me an answer of C. All right. Let's keep on moving. Okay. Which of these edges are not at maximum capacity? So let's think about this. This is like that example with the number 5. What I'm going to do is take a bit of time, and I really stress to do this. Look at every possible sequence the water could pass through this. So it could go through S, A, C, T. Or it could go through S, B, CT. Or, and there's a reason I'm doing these in all different colors, I suggest you do something like this too. You could go SBDT. So they're the 3 different ways the water could pass through this network to get from the source to the sink. So on each one of these now, I'm going to look at what the most amount of flow you could possibly get. So let's look at the water path through SACT. All right, SACT. The smallest pipe is 20, which means the most water could pass through any of those pipes on that path is 20. Now we do the same thing with my orange sequence. SBCT. This one, my smallest pipe is 15. So 15 is my most amount of water to pass through those. Now this next one here, looking at my blue, SBDT, smallest pipe is 25. So 25 can only fit through. All right, so let's have a look now. It wants to know which edge is not at its maximum capacity. So I'm going to go through and highlight any that are not at their maximum capacity. So SA is one because it could be at 30. It could be at 30, but it's not. It's only at 20. So this is not at its maximum capacity. 2020. So AC, the edge AC, it's definitely at its maximum capacity. And CT, this one here, it's definitely not at its maximum. It could be doing 50, it's only doing 20 or 15, depending on which route we take. Same as SB and same as BD. The rest, though, are at its maximum capacity. So now, which one of those is in our answers? So CT, BD, or SB, it is CT that they've put here. So that's our answer. Now, if they asked you to find the minimum cut, what a lot of people think they have to do is different to what you should actually do. If you have to find a minimum cut, it's really easy once you have all of those maximum flows labeled. I always suggest when you get a flow question, put that sequence on like I did there, and I would normally, which I forgot to, put those values there. The minimum cut, and this is something to put on your summary. I could test different cuts. I go, okay, I could cut over here, yep. I could cut over here on the end somewhere and test all different places you could cut and then decide which one had the smallest. Yeah, it's going to take you a while, and I bet you on more difficult networks, you probably still get it wrong. So there's a little theorem that says the minimum cut is always passing through all saturated edges. So now, when you go to the trouble and do what we've done and labeled all of our max flows everywhere, draw a line that passes through all the edges that are saturated. And what I've done is I've actually already highlighted the ones that aren't saturated from the question we've just done. So let's have a look. It would pass through this line, and this line. That is my minimum cut. So our min cut, if this is what they asked, and they definitely could, min cut would be 20 plus 15 plus 25. So our minimum cut is going to be 60. Okay, now notice the maximum flow through the entire network is all of these because we labeled them before as all the maximum amount of water. Now remember, up here on my little summary scan, this theorem here, minimum cut equals maximum flow. And notice minimum cut, 20, 15, and 25 equals maximum flow. So that's how it works, okay? So if you know the minimum cut, you can work out the maximum flow. If you know the maximum flow, you can give them the minimum cut. So let's see how we can do that in questions now. All right, part one, what is the capacity of the cut? It's going to be, let's check our car passes through this one. Yes, it does. Going left to right, in and out my passenger. Passes through this one. Yes, it does. Passes through this one. Yes, it does. They all go through the passenger, out the driver. So I count them all. So all those edges are counted. So it's just going to be the addition of those. So it's just a matter of making sure that when you are doing them, you're including only the ones where it comes through the passenger, out the driver. Very good HSC question would put it through one where it doesn't. And then so many people make the mistake and accidentally add that edge. All right, part 2, calculate the minimum cut. All right, how can we calculate the minimum cut? Well, we could throw a bunch of different cuts all through it, see where we reckon, add them up, see which one's the smallest one, and hope we hadn't missed any. No, let's not do that. Let's have a look at all the possible sequences. So pause the video now, and just like we did up here, where we wrote the 3 different types of sequences, this one's going to have 5. Okay, pause the video and see if you can work out, or just write and try and do in different colors or little symbols or something, the 5 different routes you can take. Okay, so they're the 5 different routes. So I've just gone along with my eyes and looked at the different ways you can get from the source to the sink. Now I'll do the first one with you again just to get you started. Let's look at OPS. Going along OPS, if the water's going along here, the smallest flow, the maximum flow along there would be 7. Okay, so label the 7s all over it. Then O just to R, O through R, it's going to be 14. So 14 and 14. And even though, notice how I'm still putting the 14 over the 14 and the 7 over the 7. I'm still putting it even if it doesn't change that number necessarily. And that's to help you identify where to put your cut eventually. So keep going now, pause the video and fill in the rest of them for me. Okay, these are the values you should have gotten. The question says, what's the minimum cut? Well, you could go through now and find the saturated edges and put your cut through it, or what's the minimum cut theorem say? The minimum cut is the same thing as the maximum flow. The maximum flow is all of these added together. So it's just a matter, and it's 2 marks, so I would make sure you're showing enough in your working to get those 2 marks, show where those numbers come from, exactly like we have there. And when you put all of those together, one thing I'm going to do though before I do that addition is just make sure that yeah, I would still do the cut just to make sure that your car runs through, when you're doing your passenger and driver side, doesn't run through any unnecessary ones rather than just adding this up. So let's do the cut first. Even though we know it's how to get it, we need to double check with the cut to make sure our car doesn't go through anything it shouldn't. So let's see, where are our values now? One thing, this is where, back up here in my summary, notice how I had greatest number? So I said it was a saturated edge when the number equaled the number. So when you have like 14 and 14, when you've got them labeled next to each other, we know that's a saturated edge. So it's with the greatest numbers, because now let's look what I mean by that. Notice how here 14 has 14, but it also has 4 and 3 next to it. So if the greatest number out of those other 3 numbers I've put around 14, if I take my greatest number, okay, so 9 and 9 works. I think that's the only one. Yeah, so it's always the greatest number out of the numbers you throw around it, and then if that is your saturated edge, if that is the same as the original number, it's a saturated edge. So I've got 3 and 3 as well, I got 4 and 4 as well, and 7 and 7. So now let's look at my cut. If I had to draw a line through those, firstly, is it possible to get a cut all the way through those? Straight away I'm noticing something. I can't get a cut through each one of those lines because I'm going to have to turn around. It's not going to work through each one, or do a loop somehow. So let's think about this logically. If I want the water to stop between the source and the sink, which ones would it need to go through? Notice how and I'll make this nice and big, if I went through here, through here, through here, notice how the water has stopped the sink going over, it stopped it coming through here, stopped going down. There's no need to go through 4. So I don't need to include 4 in it. So what do I end up left with? Yep, so not the 4. So now So we also don't need to include 3 because notice how the water's being blocked off through 7, it's being blocked off through the 14, and it's also being blocked off through 9. So 3 is also another one we don't need to include. So our addition of that is going to make our minimum cut. Part 3 I've already done because I used part 3 to answer part 1 and 2. So I've already labelled it on there. You would just have to redraw it in your HSC. So just be mindful of that when you have found all the roots in here, looking at your saturated edges, you do need to check through the little Carr theorem and see which one makes logical sense for where the water needs to flow.